See a picture up on the board right now. Describe to me what's happening in this picture. Somebody tell me something about what's happening in this picture. Happening or what's happened already in this picture. Yeah, a plane flew by? Okay, so we know that a plane has flown by. One plane? Actually, two planes, right? Okay, two planes have flown by. This is what we call a contrail or a condensation trail that follows it. It's not actually smoke that follows it. Okay, it's condensation that follows it. It's a cloud, literally, that follows the airplane. Okay, liquid that's coming out of the plane condenses and forms clouds. Okay, so we know that two airplanes have flown by. What do we know about those airplanes? Traveling what? Okay, they're traveling fast. Otherwise, they wouldn't stay in the air. Yeah. What else do we know about them? Yeah. Okay, so this one here looks like it's more recent, and we know that because the clouds haven't had a chance to spread apart, right? Is it traveling this way or this way? Hard to tell on that one, isn't it? Hard to tell on that one. It could be traveling up and to the left or down and to the right. We're not really sure, but this one definitely appears to be traveling this way, right? Because the cloud's spreading out away from it. Anything else? Did they hit each other? No, we know they didn't hit each other because you can tell by the trail that follows it, right? Something else I can tell about this one. Yeah. It looks like it was at a lower altitude because it looks like it's in front of the other one. Yeah, it looks like it. How much, we're not sure, but it does look like at lower altitude. Looks to me like this one as well. This one has two engines on the plane, right? This one, I'm not really sure about because it happened so long ago. Bottom line is there's a lot of things that we can determine about this picture without ever having seen anything to do with what causes it. Right? I asked you, what is this? And you guys told me that two airplanes flew by, two engines, one of them. They didn't hit each other. One was at a lower altitude. One flew by more recently than another. All kinds of things you told me about this without ever having seen the airplanes. This is how we study subatomic particles, like sub-atomic particles, like things that make up protons and neutrons. Do you know that there's things that make up protons and neutrons? Okay, up until today, we've pretty much told you, last day of Physics 30, we pretty much told you that, well, protons, neutrons, and electrons are as small as they get, right? Well, they're not. Electrons are, but protons and neutrons can be broken into smaller particles. How do we observe? How do we study those smaller particles? Well, we do it in a similar way to this because we can't observe them directly. So we observe trails. We observe their trails like we observe the contrail from these airplanes. We use what's called a particle accelerator. We accelerate charged particles like protons to crazy high speeds. I'm talking like 99.99% the speed of light, like ridiculous high speeds. The reason we give them such high speeds is so they get a tremendous amount of energy. And the reason we want a tremendous amount of energy is because we want to literally smash these things apart. If two cars are in a parking lot and they hit each other at 6 kilometers per hour, they scratch each other. If two cars are on the highway and they hit each other 100 kilometers per hour, then they smash apart into thousands of pieces. And we see what made up those cars. We see the composition of those cars. Bolts that flew off, internal pieces that flew off, right? Plastic pieces and parts of the car. If you want to find out what makes up a proton, then smash it into another proton. But do it at a high enough energy to overcome, to break the bonds, to overcome the nuclear forces. And then once we've done that, once we've smashed them apart, because we have these protons moving at crazy high speeds, approaching the speed of light, then we got to observe indirectly what we got, what comes out of it. Not as simple as just, two cars smashing each other, go pick up the pieces and say, oh, I didn't know that piece of plastic was part of this car. Now I do. Not as simple as that. We can't observe it directly like we do with crashed cars. We have to observe it indirectly, using one of two things. Well, one of two traditional methods. Now there's digital methods, right? But the cryo chamber. A cryo chamber is a chamber where this collision has taken place between these two charged particles. This chamber consists of air that's like purified of the dust. There's no dust. It's perfectly filtered, but it's supersaturated with water or alcohol. What does that mean, supersaturated? Pardon me? Yeah, it's like ready to rain, right? It's like ready to rain water or alcohol. Now these charged particles are, this is not a real name for these, but this is what I call them, the subatomic. The particles that were produced when we smash these particles together. When you smash protons together, well, what comes out of it? These subatomic particles. And these subatomic particles are charged. And these charged particles moving through this dust-free, supersaturated cloud chamber ionizes molecules, turns molecules into ions. And these ionized molecules cause the vapor, what you had that was a gas, a supersaturated gas, to condense into a liquid. And that's your contrail for the airplane. Okay? We trace the path of these particles by looking at the condensation trail that follows the particle. We can't see the particle any more than we could see the airplane in the exercise we just did, but we can see the trail that follows it. And from that trail, that condensation trail, we can deduce some of the properties of that subatomic particle, that thing that makes up protons and neutrons. Now we have another thing as well that we do, kind of the opposite, the bubble chamber. Bubble chamber is a liquid. So instead of having a gas that's just about ready to become a liquid, here we have a liquid that's just about ready to become a gas, that's just about ready to boil. And then we have this charged particle that's been generated as a result of this collision. The subatomic particle, as I call it, causes molecules to ionize. And then these ionized molecules, they don't cause the gas to become a liquid. They become the liquid. They cause the liquid to become a gas. Here you follow the clouds. Here you follow the bubbles that are produced as a result of this boiling. So in the first one, smash particles together, cause charged particles to be produced, subatomic charged particles. These subatomic charged particles ionize molecules, which cause the gas to become a liquid. Second one, you got a liquid that's barely above the boiling point. Subatomic particles produced during the collision. They ionize molecules, and these ionized molecules cause the liquid to become a gas. So in one, you follow the liquid, or the clouds. In the other, you follow the gas, or the bubbles that are formed. It doesn't really matter what you do. Follow the trail of either way, just like we follow the trails of the airplane and deduced properties of that situation. That there were two airplanes, that they didn't hit each other. One is at a different altitude, and so on and so on. Once these cloud trails or these bubble trails have been produced, then we introduce maybe an electric field, maybe a magnetic field. We see what happens to these particles as a result of those fields, and we can deduce properties, the speed, the radius. Based on the speed and the radius, maybe we can determine the charge to mass ratio. Maybe we can determine the speed, the mass, the charge, the whatever, right? So we can deduce properties of those subatomic particles by manipulating them with other fields and then studying the trails, the cloud trail or the bubble trail. Now, what do we get out of it? What do we get out of it, this whole deal, okay? What types of particles have we discovered? Well, there's two general types of particles. We call them fermions. and bosons. And if you look in the bottom right-hand corner of your data sheet, it talks about first-generation fermions, and it lists some examples and it lists some charge. Okay? That's where that term comes from. Bosons we don't study in Physics 30. They're what we call force carriers. They act as glue to hold matter together. An example of a fermion would be, of a boson would be a photon. Well, I mean, I shouldn't say we don't study bosons, right? We do. We study photons, but we don't need to know about their category of bosons. Another one would be a gluon. All kinds of examples of these things that are force-carrying particles, glue that hold matter together. You guys ever heard of the Higgs boson? It was hypothesized for decades, but only first observed just a few years ago in the Large Hadron Collider. Straddles the border between Switzerland and France. We finally saw it just a few years ago, just 3 or 4 years ago. Okay, that's a boson. Okay? Responsible for mass. Okay? Now, what we focus on here are the fermions. And fermions are broken into 2 categories called leptons. Leptons and hadrons. Leptons are particles that are not mediated by the strong nuclear force. Okay, they're not mediated by the strong nuclear force. In other words, strong nuclear force, remember that force that we talked about in radioactivity? It's an attractive force between protons and neutrons, but electrons aren't affected by it. So electrons are examples of leptons. They're fundamental particles. Doesn't get any smaller than that. They're not mediated by the strong nuclear force. That's it. We've got electrons. They're an example of leptons. We've also got something called a muon. Okay, we've also got something called a tau. Now, in addition to that, we have an electron neutrino, an electron antineutrino. Those are the neutrinos that we talk about and that we've been talking about. And whenever we talk about a neutrino, it's an electron neutrino, because there is actually a muon neutrino as well, and a tau neutrino, and a muon antineutrino, and a tau antineutrino as well. But the neutrinos and antineutrinos that we talk about are the electron neutrinos and antineutrinos. We do have to know this. The electrons are not mediated by the strong nuclear force. They're not affected by the strong nuclear force. And they're fundamental particles that don't break down any further. We don't need to know about the muon or the tau. Hadrons are mediated by the strong nuclear force, and they're made up of quarks. Now, there's a couple subcategories there, baryons and mesons. Baryons are made up of 3 quarks. Mesons are made up of a quark and an antiquark. So when I was talking about those subatomic particles, I was talking about quarks. Quarks are the subatomic particles. An example of a baryon, which is in turn an example of a hadron, would be a proton or a neutron. There's examples of mesons as well. I'm not going to list any because all we need to know really here is this. Now on your data sheet it does list a few different kinds of quarks. So I'm going to just go off to the side over here and mention that there is the up quark. That has a charge of plus 2/3 of the elementary charge. You don't need to memorize that because it's on your data sheet. And there's the down quark that has a charge of minus 1/3 of the elementary charge. And there's also the antiquarks. The anti-up antiquark the anti-up antiquark, which has a charge of negative 2/3, and an anti-down antiquark, which has a charge of positive 1/3. But again, that data is on your data sheet. You need to be familiar with that, but the data is on your data sheet. There are other types of quarks as well. There's the top quark, there's the bottom quark, there's the charm quark. And as if you think it couldn't get any stranger than some of these names, top quark, bottom quark, charm quark, there's the strange quark. It's the opposite of the charm quark. But those we don't need to know about. So what do we got to be aware of in Physics 30? There's leptons, which are not mediated by a strong nuclear force, electrons, neutrinos, antineutrinos. 1 second here. There's the hadrons, which are mediated by a strong nuclear force, and they're made up of quarks and antiquarks. And then some examples of those would be the protons and the neutrons. The proton, look, there's 3 quarks, and the proton has a charge of +1, so it would be up, up, down, 2/3, 2/3, and negative 1/3 gives me 1, which is a charge of a proton, right? And a neutron would be up, down, down, 2/3, negative 1/3, negative 1/3 adds up to give me 0, which is the charge of a neutron. Does that make sense? Okay, so only write down what's in purple there. What's written in purple, circle in purple, that's all you need to know. But for perspective, if you ever hear any of these other words, at least you know, like, kind of, hey, I kind of remember where that fits in the grand scheme of things. All right? All right, that's it.